These are the notes for Unit 6, Day 10, and we are talking about, I know it's labeled imaginary friends, but what we're really talking about is something called, and this is kind of, I'm going to put this in brackets, what we're really talking about are complex numbers. It's really probably a more appropriate title for this section is complex numbers. We call them imaginary because we use the letter I to stand for what we call the imaginary part of this complex number. So what we're going to start out, because we deal with complex numbers the same way we deal with any typical binomial. So we're going to start out with something that you're familiar with, and that is combining two binomials. So these are binomials. Binomials means two terms. And so we have, in each one of these terms, if you notice, right, we have a number and then a variable term, a number and a variable term. And so when we've done this many times, right, we can combine these by combining the like terms. So we combine the number terms to make a 2, and then we can combine the variable terms to make a 7x, and that 7x is positive, so that becomes 2 plus 7x. And in similar fashion, we've got two binomials again. And we can combine like terms. We've got 1 minus 4, which is going to be negative 3. And then we're going to have negative 3x minus a positive 3x, which is negative 6x. Right, it's negative 3x minus 3x. And so we've combined terms like this for years. And then we've also multiplied them, right? This is where we expand. We could consider these two factors, but again, we have two binomials again, and when we multiply them together, we create that quadratic, right? So we can go 3 times 5, which is 15, and then 3 times negative 4, which is minus 12x. That creates the top claw. And then we can go x times 5, which is a positive 5x. And we can go x times minus 4x, which is a minus 4x squared. And then we can combine the like terms here. And we get 15 minus 7x minus 4x squared. Okay, and so it's just combining like terms with binomials, right? We haven't really even started talking about these imaginary friends, so to speak. And of course, when we multiply things, like in part C, we make quadratics. And as you can see down in question 2, we're solving quadratics. So we know this, we were familiar with this technique, right? In this point, we can do on part A, we can do a square rooting technique where we say x is equal to plus or minus 3. And here in part B, we're going to have to do a little more math first, right? We're going to have to add 4 to both sides. And we can get 3x squared equals 27. And then we can divide by 3. So we can isolate that x squared, or that power of 2, so to speak, equals 9. And notice now we're back where part A was, so we're going to use that technique. X is equal to plus or minus 3. And we can do a similar technique on C, right? Subtract 2 from both sides. We get 1/3 x squared equals 3. And then we can multiply each side by the reciprocal of 1/3, which is 3. and that gets us x squared equals 9, and surprise, surprise, we're back where we were in part A, so we're going to use that strategy to find our solution, right? These are just modifications to come up with the same answer. And then we have part D, which looks a lot like part A, except that it's a minus 9. And so, you know, it wouldn't be too far of a stretch to say, well, it's so similar, it would be nice to use the same strategy, square root both sides. And that's exactly what we do. Okay, the problem is if we try to square root a negative 9, square root a negative 9, we end up with a calculation error. It says non-real answer. So if you notice that that error I'm getting on my calculator, it says non-real answer. That means the answer is imaginary. It's not real. I know it sounds a little silly. It's technically it's complex, but it can't be solved using the numbers on the real number line. So we need a technique to kind of process this and identify it as a non-real answer. And that's where the imaginary notation, I'm going to call it, comes into play. So wouldn't it be nice if we could just say, well, why can't we just call this x, because that's what the square root of x squared is, and then why can't we just call this the square root of 9 times the square root of negative 1? Then we know this. That is x equals plus or minus 3, but we don't know this. So what we do is, since that's not part of our real numbering system, we call that an imaginary component, and we call it I. And that's what I stands for, is the square root of negative 1. So we can express this then using a real numbering system, 3, plus or minus 3, and then the I is representing that negative that we can't process on our calculator. And so that's basically just telling us that we have a complex answer. So why can't x squared ever equal negative 9? Well, let's just think about that. X squared is a number times itself. That's what x squared is. And so 3 times 3 equals 9, and negative 3 times negative 3 equals 9. But we can't take a number and multiply it times itself. Looks like a negative there. There we go. We can't take a number and multiply it times itself and get a negative number. So, so that's why we know that we have to kind of abandon the real number line and work in this complex world with imaginary answers, and that's what the I designates. That's what is designated by that I value right there. Is that the I stands for the square root of a negative 1. It's saying to you that, hey, I have a negative underneath my radical, and that's how I'm going to express it. And so what we can do then is we can work within that system. Now that we know what I is, we can filter out all of our negative signs underneath our radicals and work with the numbers and then follow it up with that imaginary designation. So that being said, let's take a look at how we can get different values using just that imaginary component I. So we know by definition, because it's convenient to define it as such, that I equals the square root of negative 1. Well, what happens if I take that and square it? So what happens if I take I and square it? Well, that means I'm taking the square root of -1 and squaring it. And that means that the radical disappears, so it must be -1. Well, what happens when I cube it? Well, that means I'm taking I squared, which is -1, I squared, and I'm multiplying it times I, which is -1 times the square root of -1, which is -1i, or -I. Well, what happens if I take it to the 4th power? Well, that's just I squared times I squared, which is -1 times -1, which is 1. Well, we can start filling in down here now. So this is -I, this is 1. What happens when I do I to the 5th? Well, that's just I to the 4th times I. Well, I to the 4th is 1. And I is the square root of -1, but I'm just going to leave it as I. So I to the 5th is just I. And we're back to what the definition of I was, which is -1. So we have this graphic that we can kind of set up here. And it's circular, basically. And we can just say, okay, I to the 0 power is 1, and I to the 1st power is just I, and I to the 2nd power is -1, and I to the 3rd power is -I. And so as we accumulate powers with our I, we can just keep using this circular pattern. So if this is where I cubed is, then here is where I to the 4th is. So this is I to the 4th. This must be I to the 5th. This must be I to the 6th. This must be I to the 7th. And this must be I to the 8th. And this must be I to the 9th. And this must be I to the 10th. And this must be I to the 11th. And we can keep going around that circle where the horizontal axis, it looks like the regular number line, right? This horizontal axis, we got -1 here on the left, +1 here on the right. This is like the regular number line. And this vertical axis looks like the imaginary number line. We're going up I or down I. So where does I to the 16th fall? Well, 16 is a multiple of, is it a multiple of 4, 5, 6, or 7? And it's a multiple of 4. So I to the 16th falls here. So I to the 16th is I to the 4th times I to the 4th, that's I to the 8th, times I to the 4th, that's I to the 12th, times I to the 4th, that's I to the 16th. So this is 1 times 1 times 1 times 1. So I to the 16th must be 1. So I to the 17th must be up here. If this is I to the 16th, I to the 17th must be up here. So we can find that pattern then and deal with any power of I. And it's going to be one of those 4 values. And that comes in handy when we do multiplication. So if you notice, question 4, I'm trying to zoom out here, it's like question 1, but instead of x's, I have i's. And we deal with them the exact same way. We look at it as a binomial, right? We look at it, as a binomial, 2 terms, and we combine like terms. We combine like terms, and we do a claw type of process here. So let's try that with these expressions. So these expressions, although they are binomials, right, we still have a binomial here, and we still have a binomial here. We still have two terms in the brackets. We call this a complex expression. That's the general term for it. So let's combine, let's see, I'm just going to get my color coding here, orange and pink. Okay, let's combine these things. Okay, so let's go after the number, the real components. So -1 plus 3 is 2. And then let's go after the imaginary components. That's these guys. 2 plus 5 is 7, so this is 7i. So it looks just like number 1 above, right? But it's got an I instead of an X. Same with B. It's going to look like number 1 above. We're going to combine these binomials. We're going to combine like terms. So we'll take the real components. 1 minus 4 is -3. And minus 3i minus, minus 3i minus 3i is -6i. And then when we multiply, we're going to do our claw. We're just going to adapt that claw a little bit. So we're going to do 3 times 5, which is 15. And then we're going to do 3 times -4i, which is minus 12i. And then we're going to do I times 5, which is plus 5i. And then we're going to do I times minus 4i, which is minus 4i squared. And this is where we're going to have to do a modification here, because we know modify, because we know I squared is equal to negative, there we go, -1. So what we're going to do as we simplify this, we got a 15 here. We've got combining these terms, which is minus 7i, and then simplifying that last term, this is going to be minus 4 times minus 1. So what happens then is that I squared term becomes a real term. And so this is still minus 7i, so that this minus 4 times minus 1 now is plus 4. So fully simplified then, this is going to be 19 minus 7i. Notice it simplifies back into a complex term. So that complex expression looks like a plus bi, where a is what we call the real component, and b is the imaginary component. And everything will simplify down to that complex expression, no matter what the power is that you have on that imaginary number I. Okay, so let's take a look at the learning targets here. We've hit on a couple of big ideas. The first learning target is that we have this, I'm going to call it the imaginary number. The first one is that we have an imaginary number. And that imaginary number is I. And its definition is that it's the square root of -1. And its purpose is to allow us to deal with radicals that have negatives in them. That it allows us to deal with we having to take the square root of a negative number. We also know that I squared is just 1, and a -1, excuse me. It gets rid of that radical. And we also know that we can reduce anything with that graphic from the previous page. So maybe I take this and duplicate it and bring it over here. Maybe make it a wee bit smaller, and I put that right there. So we have that, that wheel where we can process any power of I. Okay, the second learning target 2, is simplifying radicals. So if we have a radical where we have the square root of -7, then we process that as the square root of a +7 times the square root of a -1. And in this case, actually I'm going to leave it as a +7. In this case, when we look at processing that, we know the square root of a +7 could either be plus or minus. And then the square root of -1 gives it the imaginary designation. Or we could, square root 7, we could give it its decimal equivalent, plus or minus 2.646i. And then learning target number 3, because we're talking about radicals, I'm going to introduce, because we're talking about radicals, when we do process that with a negative square root, we get that plus or minus. Notice we get 2 answers. So the square root of -7 is 2 answers. Just like the square root of -9 is plus or minus 3. The square root of -7 is plus or minus 2.646i. So it's 2 answers. And so every time then you have an imaginary component, you get 2 answers. Just like anytime you square root a positive number, you get 2 answers. So we call those conjugate pairs. So the square root of -7 has 2 answers. And one is plus 2.646i, and one is minus 2.646i, and those are called conjugate pairs. And in general, the conjugate pair is, if we write it the whole complex number, the conjugate pair is a plus bi and a minus bi. In other words, that imaginary component, that I part, is either plus or minus. And we'll see that going forward as you check your understanding. We'll see that going forward here. So I'm going to do the check your understanding. I'm going to do A and C, and you're going to do B and D on your own. I think these are pretty worthy check your understandings to do. So in A, we're going to square root both sides because we have x squared equals -16. So we can square root both sides. We can use that technique right out of the gates. We get x equals square root of 16 times square root of -1. Square root of 16 we know is plus or minus 4. Square root of -1 is I. So this is plus or minus 4i. So that's your conjugate pair. Okay, so go ahead and pause the video and do B. All right, if you started up the video, I'm assuming that you've completed B, the exact same progression in steps. We get plus or minus the square root of 12. Wait a minute, I'm skipping some steps here, sorry about that. That we process that as the square root of 12 times the square root of minus 1. And so that's going to be plus or minus the square root of 12i. Notice the i's on the outside of the square root. And then you could simplify that into a decimal if you wanted to. Okay, let's look at C together. So we've got a few steps here. I'm going to have to subtract 15 from both sides. I get 2x squared equals minus 50. I'm going to divide by 2 to isolate that x squared term. Get x squared equals negative 25. I'm going to square root both sides. And I'm going to get x equals plus or, again, I'm skipping steps here, right? We're going to square root of 25 times the square root of negative 1. And that's going to be plus or minus 5i for that answer. And then let's look at D as together, because I think it's a bit of a stretch here. We subtract 5 from both sides, we get negative 16. And we get x minus 3 quantity squared. And we're going to follow that. We've isolated the power of 2, so we're going to square root both sides at this point. So we get x minus 3 equals, and this is the square root of 16 times the square root of negative 1. So that's plus or minus 4i. X minus 3 equals plus or minus 4i. So we have two answers here. We're going to add 3 to both sides. And we're going to get x equals 3 plus or minus 4i. So there's your true conjugate pair. We have a real part, and we have an imaginary part. Okay, and our two answers are 3 plus 4i and 3 minus 4i. And together that makes a complex solution. And so notice we have that plus minus pattern re-emerging because of that, taking that square root of a number, right? That's where we get that plus minus pattern emerging. And so going forward, you might be able to anticipate this. This is going to become a component of the quadratic formula that we're going to be encountering in, I think, day 11. Okay, so now that we've done that, check your understanding, go ahead, and I've got the answers here in red, but go ahead and try these algebraic operations